You can introduce the speaker.
Sure. Good afternoon, everyone. Thank you for joining this NITheCS seminar talk. It's a great. It's a pleasure to introduce Prof. Fabio Dercole from Politecnico di Milano, which is the Polytechnic University of Milan, where he completed his degrees way before me in 1999 and 2003. I was about 10 years after that. Fabio was actually my PhD supervisor, so we did work together for at least those years, but also afterwards. And he's professor in automatic control, so linear systems, that's undergraduate, and also nonlinear dynamics for postgraduates. And today he's going to talk about a feature of nonlinear dynamics, which is deterministic chaos. And we are hopefully all looking forward to hear more about that.
Okay. So thank you.
Can you check if the recording my voice in some way? Yes, of course. And then I have to say ciao to Sandra, that they told me you are connected. I don't know if you can speak, but hello. And let's see soon. So again, thank you for being here. It's going to be maybe a technical talk, but actually I like to say that it's important to talk. Because essentially the chaos has many features that you might know. Essentially the two most important are the sensitivity to initial condition and the accounting process. Let's say a deterministic process. That could be even a stochastic problem. But let's stay in the simple deterministic context. If there are two nearby initial conditions, you know that the two projecting two possible futures are attracted towards the target attractor, the two stories, they diverge. Sooner or later, they diverge. Space, space. So meaning two very different futures are from two very initially close by conditions, which is the very well known butterfly effect. I'm going to say, what if now butterfly Africa wings or not? The atmosphere of the Earth is very similar initial conditions. Everything is the same, but that specific butterfly flipping or not flipping now the wings. So two very initial conditions. In one future there is a hurricane at some point in Florida, in the other it's not. Two very different futures. And that's the sensitivity to initial conditions that all complex dynamical processes do have. You cannot avoid. That means that complex dynamical process, even though they are deterministic in the roots, if you know all the roots of physics, assume you know all the roots of physics up to quantum and microscale, then you can have the model of the universe. I mean, the fact that that your model is deterministic or stochastic is the method of choice of model. It's nothing about nature. Nature is not. It's neither deterministic nor stochastic. It's just nature. We ask us what it is, it's that it works, the metrics, and also. So we don't, as mathematician, we look, we observe, and we model. We can model the mystical, stochastic, or the model. So assuming you know all the rules, then you are able to make the deterministic model, but it will be so complex that you cannot avoid this sensitivity. But this is nothing to do with control. It's what is chaos. It's the results of a complex dynamic. So sensitivity to initial condition is one feature, one of the main two features. The second is the complex geometry. The attractors, the object for which the trajectories are attracted is complex geometry. So when you know that chaos is unpredictable because it's sensitive to initial conditions and nice to see somehow because they're nice pictures. Okay. And this picture somehow reminds you of the butterfly effect. So Lawrence first is actually a designer here. And I like it a lot because it has Lawrence as the origin of chaos, but also this very nice tool for studying chaos. It's a two-dimensional simple map called the Smale horseshoe. Because Lawrence actually found chaos by simulation. Even now, he thought it has a bug in the code. He was simulating three-dimensional equations, and then the trajectories in the prints, not even in the graphs, printout. So the simulation was a long printout of numbers, there were no graphics in the 1963. So he was checking all these numbers, and they were not going to the equilibrium, not stabilizing, not even repeating after a while, after sometimes. So he said, there is some bug in the code. Actually, the first count. So, but then the mathematics of chaos is being developed by Smale. American mathematician. And this map, I'm going to use this map because if you want to study mathematical definition of chaos, the simplest way to do it is to do it through this map, which has this horseshoe shape, which is in the background. So I reminded you already the two main features of chaos: sensitivity to initial conditions and complex geometry. But one that has been always taught to me without ever showing me proof is the, or maybe I'll make a step back. A third feature, maybe less exotic, is that there is at least one project that is visiting densely the full plot. Densely means that this trajectory in time goes arbitrarily close to any point, each point of the plot. Essentially, it means that you visit all of it. You don't miss anything. Because you go as much close as you want in time, you have to wait. So if you wait enough, you go arbitrarily close as you want to anything. Maybe you don't visit exactly all of them, but mathematically this means almost all. All means the measure of the point to visit is one. It's the total thing, the whole thing. Okay, there are such trajectories. It's not difficult to see that there are even in the Smale horseshoe map. But my question, that is a very well-known question, with no formal answer to me, is: are those dense trajectories the majority of trajectories, or just a few, or just one? So essentially, if you take an initial condition at random, what is the probability that the trajectory starting with that initial condition will visit the water, will be dense trajectory? Or in other words, for those initial conditions producing dense trajectory are that they have measure 1 in the attractor, measure 0, or something in between that would be very good. Let's say you have probability 1/2 that you pick an initial condition, half initial condition they visit densely, and the other half they only visit a piece. That would be very weird. I would expect either 0. I mean, there are some initial conditions visiting the whole thing, but they have measured 0, like the rational numbers. Those initial conditions, if we go, I tell you, the answer is 1. So you have probability 1, so almost surely you take an initial condition, that trajectory will visit the whole thing. And this is what I've been always taught. I don't know about you, and I had very great professors in nonlinear dynamics, not only in Milano, but I've been doing a postdoc at my university, big guys. Steve Strogas, the book, and John Gennari, the other book, very hard book from Springberry classification. Those two has been my teacher and they didn't show me a bit. So after many years, they said, okay, and I don't do research. I do research on applied mathematics. So I apply mathematics, I simulate, I found chaos, but I never did real theoretical research. This is my first little work, but I said, okay, I want to try to show whether this would be this initial condition, visiting, production trajectory, visiting the whole thing densely, are those trajectory have this initial condition measure 1 or 0. For sure, there is one. No, there are many others because they are all different. In the definition of attractor, there must be at least one trajectory visited. That's the definition of attractor. Otherwise, it's not. But my claim is that the set of initial conditions using such trajectories has measured 1 in the set, so almost all. But each of them will produce a different orbit, because actually they diverge. Each initial condition is in one-to-one relation with one orbit. Okay, and I told you already that the answer is yes. So almost all trajectories that are attracted out of the attractor, they see the work. They visit the exterior. So then the rest of the talk is just a proof. That we have also to, I have also to remind you what is the Smale horseshoe. It's a common theoretical tool for chaos, but it's review it. Yeah, of course. No, but if it's an attractor, again, back to the definition of attractor, it should be an open set containing the attractor from which all, not almost all initial conditions produce protected attractor that converge. So we are my set of initial condition is a subset of the basing of attraction. So to me, we are working within the basing of attraction of the attractor. So all, not even but one, all the initial conditions produce projections that converge to the attractor. But the question is, are they visiting the whole thing or just a piece? So for example, you know that within the attractor there are cycles, unstable cycles of any period, and those are all saddle cycles. It means that stable manifolds converging to the cycle and unstable manifolds converging to the cycle manifolds in time. Okay. This is a cycle within the attractor. There are initial conditions producing trajectory converging to this because the set is attracting some. So there are, then you attract the cycle. So you don't visit one thing, just visit this piece. But then this set of initial conditions is zero. And there are even many other complex trajectories not visiting the whole thing, but my theorem will show that those have measured zero. Actually, the proof is to show that those have measured zero. But consequence, you have the rest. But now I'm not the PowerPoint is not proceeding. I don't know why. Okay, now it goes. It was a bit sleep. Okay, I told you that I didn't do research, theoretical research on chaos, just to introduce myself to people and been applying. It's not really studying, but it's practical. And actually, by doing my application, I discovered on my scientific life two new concepts. One in evolutionary dynamics, through modelization, of course, I proved that natural selection, so mutations and selection, is not an optimizing process. Also, evolution does not optimize anything, even in a static environment, even in an environment where there are no environmental restrictions, constant temperature, constant heat, constant resources, constant everything. Evolution is not optimizing, and actually you can have evolutionary cycles, meaning that mutation that win, so new type replace the previous one, another mutation, another mutation, and each time the winner is better than the previous one. So you might think that some fitness is increasing, but it's not the case, because each time you have replacement, the environment, though it is static, is different, because we have a new type. And this can be such that at a certain point you make a cycle. That means that you go back to a type that has been defeated maybe thousands or millions of years ago. But now is the winner, because cycle. And actually, you can have even chaotic evolutionary attractors. Meaning that our phenotypes, for example, the angle of our backbone, if we go like this, then we have been evolving like this, and maybe if we are on a cycle, we will be evolving like this. Or if it's chaotic, we will evolve in density. Okay, so chaotic evolutionary attractors. Also, the law of stories can be described by this chaotic attractors of the feelings. The feelings are variables. You know, they can reach a plateau, like you, look at the positive, the negative events. You can love to a certain level, you can hate to a certain level, constant time, you can also completely level, or you can have a chaotic wilder situations. And okay, so you can have chaotic attractors, describe the log stories. This is actually one. So, a little bit also, not that my PhD, but this book was after PhD, but after we worked together, maybe more in evolutionary dynamics. Actually, the law of dynamics is actually the original idea of our common mentor professors. So this Sergio Hernandez is my PhD advisor, also part of the PhD advisor of the idea of modern process is Sergio. And more recently, I used the deep learning to predict, to challenge artificial intelligence to how far you can predict certain accuracy. You can go pretty well. So we can predict up to 7, 6, 7 Lyapunov times. It's the inverse. The inverse of the Lyapunov exponent is a time. And if we can go up to 6, 7 Lyapunov times, which is of course the largest is the Lyapunov exponent, so it means the exponential rate of the closed function conditions. The smaller is the inverse, the Lyapunov time, so the smaller is the more answer. That's very nice. So just to say that this is what has been doing, no theoretical work of chaos except this. So now we go to the horseshoe. So the horseshoe map is defined on the unit square of the plane. So that's x, y, and state variables. It's only defined starting from point in the unit square because we don't need it. We don't need to define it outside. It's possible. It's not because it's not a thing. But we just focus on the unit square. And the unit square I call it S squared. F is the map. So f of p is the forward image of p. You start from a point and jump to another forward image. F minus 1 is the previous image because the map is reversible. You can go forward. As a notation, let's say fk and f minus k is k image forward, k image backward. And there are no equations, not because again it's a trick, just because we don't need them. It's a graphical. There is a graphical description of f and a graphical description of image. But you can write actually to plot these pictures. I converted those rules into equations. So forward, you take a square, you squeeze it, factor 3, say factor 1/3. Horizontally, you elongate factor 3 vertically, so our points are the form. Then you bend in such a way this rectangle goes back into the right vertical plane of the unit square. Okay. Squeeze, stretch, and bend. And as you see, there are those light gray points in the middle horizontal third, which goes outside the unit square. So points here are bent somewhere here. And we forget about it. So there are points in the unit square that, as as forward image outside the square. We simply forget those trajectories. We don't follow them. To follow them, you should define the map also outside the square. It's possible. And to go backwards in time, we start from the unit square. And now we do the reverse. We squeeze vertically, stretch horizontally. You don't see it, but it's here below. And then we bend to the left. Before we were bending to the right, now we bend to the left. This right tangle flips and goes to the top third of the unit square. And again, there are points now in the middle vertical third that goes outside. Backwards in time, it goes outside the unit square. And again, we don't follow this. So we only follow trajectories that are forever forward in time in the unit square and forever backwards in time. So the initial conditions, if you want, that never leaves the unit square neither forward nor backward. Maybe this set is empty. Maybe there are no such things. There are. And there are, and actually you can imagine, you can understand it very easily from here, because if you do twice, okay, discussed already that it's not invariant because you can go outside, but there is such a set of let's call it factor lambda points, such that all forward and backwards images are in the unit square. The question is it empty? Or actually, it's even a chaotic set. It's not empty. It's a chaotic set because the apple of exponents is not. There is always a diverging factor 3 of divergence in any step forward and backwards in time. So compute the first the apple of exponent is nearly log 3 positive. So that means this is a chaotic set. I should first tell you that it's not empty. To check that it's not empty, I think we should go to the double forward and double left of intervals. And then you realize that the more you go forward, and the more you see that the x coordinate of the points, the dark gray, that remain in the unit square, they must be x coordinate must be a point in the Cantor set. What is the Cantor set is the x-axis is the clouds of points that remains if we iterate this process on and on and on along infinite times done. That means see we had a square at the beginning, then we made it 2 vertical. But let's just look at the x-axis. We have 2 segments, the first third, last third, then segment is split in 3 and you remove the middle third each time. And then again, if you go forward in time, these dark intervals, they are divided in 3 and you remove the middle third. And you continue, and the remaining points, you might think it's nothing, actually there are infinitely many remaining points. It's actually an uncounted infinite remaining points that are as much as the real 0-1 interval. It's a bit strange to understand because you remove the middle third, then you remove the middle, then you keep on removing middle third, smaller middle third. You remove a lot from the unit interval, but the remaining points are, that's a miracle, as much as the full unit interval. Same type of thing, same cardinality. Mathematicians are used to these weird things. Yeah, exactly. Since the same happened backwards in time with the vertical axis, now back to the question, this big lambda is not empty, and it's actually easy to understand that it is the set of points that have both x and y coordinates as numbers in the Cantor set. So it's the Cartesian product of Cantor set and x, Cantor set y cross, and all the crossing points are points in this lamp. So our points starting from which these complex dynamics remain forever forward and forever backwards in the in the unit square. So now we have a setup. Okay, just to remind that I gave name. Essentially, I'm using seems that I'm using 0 for bottom and 1 for up and 0 for left for vertical split, 0 for left and 1 for right. Actually, I'm not doing this. It seems so, but if you go to the, because we have to give names to these horizontal and vertical planes to play with those things. And the way we name the tricky, the smart way of giving names is not just 0 bottom and 1 up and 0 left and 1 right, but it's each time you go up, in order to identify a smaller and smaller and smaller, let's say vertical street, each time you go to a smaller street, if you go up, you reverse the, or if you go right, no, sorry, the vertical ones, we go left and right. Each time you go right, you switch the meaning of 0 and 1. So after the first right, then 0 will be an extra right, 1 will be an extra. And if you take an extra left, you don't switch the meaning. But as soon as you take, one, as soon as you take no, as soon as you take a right, you switch the meaning. Because right, the reason is that right, the right part is the part that is flipped. So this geometrical flip is described by the switching of the meaning 0 and 1. Anyway, just a trick. We use this trick. So let's play an example. So this, to reach this street, we go left, take the left third, then divide in 3 and we take the left. So this is, the street is left, means 0, 0. This is left, go to B0, and then right, so 0, 1. We took a 1, so we have to switch the meaning, but this will affect the smaller streets that are not shown. But this, for identifying this street, we go right and left, right? And then once you are in the right, we take the left. But once we go right, so there is a big 1, but then we switch the meaning. So to go left, now it's again 1. So this is 1, 1, because we did right, 1, we switch the meaning, and now left, that is 1. While if you take right, is the first right is 1, but the second right is 0. And then we can go on to identify smaller and smaller and smaller vertical and horizontal. You have this bottom, this is bottom up, this is up 1, then bottom, that is again 1, because we switch them. So with this way of naming, yes. Countable, why countable? Yes, but okay, we I would say it's a two continuous infinity because you have to identify a point, you have to identify one infinity narrow band, vertical, and one horizontal. Essentially, two coordinates in the set. And you identify one with an infinity sequence of bits. But an infinite sequence of bits is a real number. It's a continuous. With an infinite sequence of bits, you can code a real infinite one. Because let's take that each bit is a power is a negative power. The first bit is 1/2, the second bit is 1/4, the third bit is 1/8, and then if it's 1, you take it, if it's 0, you don't take it. And if you sum all these powers of 2, you get a real number. So it's a continuous. And then you have another infinite sequence of bits that identifies the horizontals, another real number. So it's actually two real numbers. Indeed, 2 points in the contour set, but the contour set is equivalent to a real. So it's two uncountable. Two continuous. Okay. Maybe we can discuss it. Now, I'm not that strong in number theory, but I would say if you truncate, and you take a street with a certain width, then you truncate, you have a finite sequence of bits. That's count. It's the integers. All the integers can discuss each integer. Okay, see your point. You say if you truncate, you have a yeah, but the number of strips is equivalent to the number in the contour set. So it's maybe we proceed, otherwise it's too long. We think about it. Anyway, this is it. It's points with both coordinates belonging to the contour set. We agree on this. Then I think it's a double uncountable infinity, but that's discussed. Now, with this naming is so powerful because now if I take the sequence of bits is giving me x in the way I call binary code. An infinite sequence of bits gives me a real x. Another sequence gives me y. So let's call sx and xy indivisible. But those sequences are coded with the trigger code. Okay? They're not exactly binary sequences. They are binary sequences, but the interpretation is the one that code. So Sx is the sequence of bits which identify the vertical strip, the vertical line, and Sy is the horizontal sequence of bits identifying with the coding that explain the horizontal line. So then a point is characterized by these two sequences or by one big infinite sequence of bits. And let's compose this by infinite sequence in this way. So the by infinite sequence characterizing identifying point P, let's call it sig squared because it's big infinite, is composed by take the sequence of the x coordinate. This is a location for big, but it's actually if you don't identify a line, vertical line, this sequence of bits become infinite. So we take the sequence of bits identifying x and we flip it. Then we put a separator just to remember where it is, and then we append the sequence of the y coordinates. So we have at the right of the separator we have bits identified by a positive index, and those are the bits that identify the y coordinate. While bits -1, -2, -3, -4 are those identifying the exponent. And once you describe point P by this sequence, by this bi-infinite sequence, going forward, that is squeeze, stretch, fold, is just move the separator one line, or take this bi-infinite sequence and shift it one position. It's a miracle. This is why this coding is so powerful. While going backwards in time, that means squeeze vertically, stretch horizontally, and go to the left, and fold to the left, is taking your bits and shift right, or move the separator one left. And this is so powerful that now we can forget about the max and just play with it. This is not my result. This is main results in the 1970s. And we can also define distance between bi-infinite sequences, but I don't have a formula so easy. Essentially, the more the bits close to the separator are, imagine to have two bi-infinite sequences, 2 points. The more the central part across the separator is the same, the more the 2 points are close. So if they are very close, they have a central part to the right and to the left of the separator, which is equal to the 2 sequences, but then there are different bits far away from the separator. The more the different bits are far away, left and right, right and left of the separator, and the more the 2 points are close.
Sorry, I just want to clarify that question. So when you move the separator to the right,
means, let me think, you go forward and back.
so that's set.
No, let me
yes. Set. So that's the piece the subset of each of the parents.
maybe the best
So
is
I'm going
to make an example of it.
Okay.
Let's say this is 0. This bit is 0. Means that to the right of the separator, you have the y coordinates. 0 means below, bottom. So it means if this is a 0, this point, remember that the bi-infinite sequence is in one-to-one relationship with points. So take a bi-infinite sequence, this is 1 point. Let's assume this is a 0. It means that this point is in the third, is in the bottom. Yeah. Let's say that S minus 1, which is the vertical is 1. So it means the point is in the right vertical. So it means that if this is 0, this is 1, the point is in this square. The intersection of the bottom third horizontal and the right third vertical. Now let's assume that S1 is 1. So it means that vertically we took 0, the bottom, and then the third upper part. So now we are, means that our point is in this rectangle. Now we go forward in time. So we have a point here whose forward image shift 0, 1. The 0 goes here, so the 1 goes here. 1 means the point will be for sure in the upper part, the image, and blah blah blah. So you can actually, the more you look at bits across the separator, and the more precisely you identify the points and the forward image and the backward image. And it's actually easy to code. And you can click and see the point move. So for example, then, now that we have this set up, it's very easy to understand the complexity of these dynamics. For example, if you take the sequence 0, 1, 1, 0, and you repeat it forever and ever, this is a cycle. Because once you shift 4 times, either the left folding time or the right, I'm used to shift bits. No, I don't want to move this, but then we have to choose one, otherwise we get. Let's fix the separator always in the middle and we move bits. Okay, so if you move these bits 4 times, then you are back in the initial point. And indeed, these are the 4 points. These are the 4 points represented. One is this. One is the point represented by this sequence shifted compositions, shifted positions, shifted. And then once you shift the 4, you are back. And this is a cycle. It's actually a second one because there is a multiplier or diagonal of exponents log of 1/3, which is negative, and log of 3, which is positive. So it has a stable manifold and an unstable manifold. And it's actually very easy because which are the points belonging to the stable manifold of this cycle? It means points that forward in time are attracted to this cycle. It's very easy. You build a sequence where this 0, 1, 1, 0, you repeat it to the right forever and ever. And then in between the separator and the initial repetition, in the first repetition of the period, you have a finite sequence of bits that arbitrary, and to the left you have an infinite sequence of bits which is arbitrary. All these points now, if you shift, all these periods will invade the whole thing. Means you converge to this cycle. But what's the dimension? How many points are in the stable manifold of this cycle? Now, how did we build this point? We said, at a certain point, we repeat the cycle forever and ever. Then we have a finite sequence of bits in between the separator and the first repetition, meaning rational number. Finite sequence of bits is a rational number. Okay, so the cardinality is a countable infinity. It's like the rational numbers. And then on the left of the separator, we have a real number. We have an infinite sequence. So the cardinality is the cross product between a continuum and a countable. But this set has measure 0 in lambda because now I'm convinced lambda is a double continuum. And indeed, this stable manifold that is a continuum cross countable has measure 0 in lambda. So there is a stable manifold, but it's just nothing. I mean, the probability to take an initial condition in the stable manifold, so converging to this cycle is 0. There is 0 chance to take an initial condition that converges, that generates a trajectory converging to this cycle. This is another cycle, period 5, and then we can even have so-called heteroclinic trajectories converging to one cycle forward in time and to another cycle backwards in time, or even oboclinic, forward and backward at the same cycle. Easy. We have to repeat on the right the cycle we want to reach forward in time, repeat to the left the cycle we want to reach backwards in time, and in between we have 2 finite sequence of bits from the separator to the first repetition forward, from the separator to the first repetition backward. So how many? 2 countable is twice the rational. Again, measure 0. So we have periodic, heteroclinic, homoclinic, stable manifold, unstable manifold, so converging the cycle backwards in time. All these trajectories are compared to the set lambda, compared to the set of all possible trajectories. And we do have also at least one trajectory dense in lambda, means visiting lambda densely, so passing arbitrarily close to all points of lambda, both forward and backwards in time. How do we do this? Remember that to be close to a point, you have to match the central part of the bi-infinite sequence. So let's build a sequence and initial conditions in this way. We have a separator here, let's build a trajectory dense forward that visit the attractor densely forward. We list all blocks of 1 bit, 0 and 1. Then we take a random bit, not a random, arbitrary, we can choose. Then all blocks of 2 bits, 0, 0, 0, 1, 1, 0, 1. Then another bit. Then all sequence of 3 bits, then another bit, and so on and so on. So if we now move to the left sequence, sooner or later, we have all possible blocks of k bits for any k. We have them all. So if I want to pass at a certain distance that I decide close to a target point that I decide, sooner or later, I will have a piece of bits corresponding to a long enough central part of that point, close to that point, that will, at a certain point, will be across the separator. Because any point, any target point I take its coding, I take the central part long enough to pass close enough to that point. That sequence of bits, sooner or later, I had it in my sequence. And the same I can do backwards in time. So there are trajectory densities. How many? How many? Well, look at these arbitrary bits that I placed in between each block or each. You can place it each block or every set of blocks. In this case, it's 4 blocks of 1 bit, arbitrary bit, 4 blocks of 2 bits. So when I list all blocks of 2 bits, I don't put extra bits in between. They put 1. But this is already enough. I have an infinite B1, B2, B3, B4, I have an infinite sequence of bits to choose forward in time, and another infinite sequence of bits to choose backwards in time. So I have 2 real numbers. Those dense trajectories are a double continuum. So that's the question. Do they cover all lambda? Maybe, because lambda is a double. And so far we have discussed nothing. We have discussed cycles, stable value, homophysics, nothing. But these trajectories are a lot, are as many as lambda. Because it's a set in which x and y are both coordinates in the Cantor set. The Cantor set is equivalent to it's a cross product between 2. It's not a continuous set in the sense that points are connected. But the cardinality is the same as the real. That's for sure. The cardinality of the Cantor set is the same of the. Oh, okay. You remove. No, that's fine. However, there are also non-dense trajectory. Maybe we can see. Can I remove this way? It seems that it flashes. Anyway, because now I'm asking to myself, okay, this is a double, this set of dense trajectory. They are uncountably many. This is already enough to say that they have measured 1 in lambda, not 4. Why? Take, for example, the Cantor set. The points in the Cantor set are as many as the real in 0, 1. But the measure of the Cantor set in 0, 1 is 0. Okay? Because measure is a Lebesgue. You have to count length of segments, and those segments they go to the power of 3, power of minus k, and they go to 0. So Cantor set is true, has the same cardinality of the real, but the measure is 0. So the probability to take a real by random and the probability that that real is in the Cantor set is 0. Probability is measured. Okay. So now those trajectories are, from the point of view of cardinality, are as many as the points in lambda. But the measure of those points in lambda could be easily 0 or 1. I want to show that it's 1. Or in between 0 and 1. So now let's discuss non-dense. So let's call D dense. Sigma is the set of sequences. Sigma is the set of infinite sequences of bits. And sigma squared is the set of pairs. So let's go D sigma, the set of sequences, including all finite bit blocks, like the sequence I put on the right. It's just a single sequence, only infinite in one direction, because it's easier to discuss just single sequence. Then, of course, then to discuss both forward and backwards in time, we should go pairs of sequences. But let's stick with one. So D is the set of sequences, infinite sequence of D, that shows that includes all finite bit blocks. It's a sequence in which you like a certain finite bit blocks, you find. Sooner or later, you find. You like another, sooner or later, you find. Like the one we did. So these are the right sequences of initial conditions of the Smale-Schumann density visiting lambda. Those are the sequences that if you place those sequences to the right, the separator, then this is an initial condition density visiting lambda. But then let's go with a tilde, which is a not logic. The set of sequences missing some finite bit block. And let's call with the argument B the set missing specifically block B. It's a infinite sequence of bit in which you will never see block B. B maybe is a bit, it's a block of 5 bits, 1, 1, 1, 0, 1. You will never find. They are both uncountable sets. This uncountable, we discussed it already, but also this is uncountable because we have to place bit blocks without, of course, putting block B. And in between, we can have arbitrary bits with the attention that those arbitrary bits should not complete a block in order to give the forbidden. So there are a few restrictions, but still is you have an infinite number of choices. That means a real. So now they are. They are disjoint sets, the union of which is lambda. So if you show that E tilde has measure 0, you have also shown this. Not in lambda, actually, in the 0, 1, no, in the Cantor's, because we are working only on single infinite sequence describing points in the Cantor's set. Then if you take the infinite, you have 2 Cantor's sets. So what I want to show is that the measure in sigma in the set of single infinite sequences of this set of sequences missing one particular block is And actually, you can simplify. It's enough to show this for a specific block, because the blocks, the finite blocks of bits is a countable sequence. So this set, without the argument, is the union of all these sets for all possible block B. But the union of a countable number of sets, or the measure of the union of a countable number of sets, is the sum of the measure of each set. So if this set has measure 0, this set has a measure which is the sum of many zeros. So we have to show that taken a specific block B, the set of infinite sequences not showing that block has measure 0 in the set of all possible units. But we have to define a measure. Measuring sigma. One possible way to define a measure in sigma is to take the bits of sigma, take a sequence in sigma. This is just a simple operator that I did. Let's associate to each sequence the real number according to the binary code, not to the tricky code that I call binary. So we take all bits sk and we multiply for the power of 2 minus 1. So this is just a decimal conversion. That's why I call it C. It's the decimal conversion of the sequences. It gives you a real in 0, 1. Okay, just the decimal conversion from binary to decimal. And then for a set, for a measure of a subset of sigma, for each sequence in the subset, we take the corresponding real and we measure the set of real in the segment 0, 1. So for any subset of sigma, that means for any set of sequences, the measure of the set in sigma is the measure in 0, 1 of all the decimal conversions that we get from the sequences in the set. And it is a measure because there is a one-to-one correspondence between the sequences and their decimal conversion. So we can look at the sequences, we can look at the decimal conversion. We can look at the sequences in sigma, or we can look at the decimal conversions that intervals. So now, is it late? I guess 1 hour. I spoke for 1 hour. This is just the conclusion. Actually, maybe it's the proof. So maybe it's for mathematicians, it's the core of the. But I think that now it's quite intuitive. So we want to show, I will tell you, that taken a block B, the set of sequences not showing B have measured in the sense that we just discussed 0 units. Okay, so just a notation with Gen B, if B is a collection of blocks, they generate by like the Lego bricks. But you can actually, it's a smart Lego because you can generate as many bricks as you want. But you have a certain type of bricks and you can compose them. Then you generate a subset of C generated by a certain collection of bricks and blocks. And for each block, I like to identify an interval of the 0, 1. The with the decimal conversion of the block, and as right extreme as the decimal conversion plus the power of 2, the negative power of 2 given by the number of bits in the block. This means that all sequences that start with this block and then arbitrary bits are numbers in this block. If you think about, because except for the decimal conversion of the finite bit blocks, what remains are powers of 2 smaller powers of 2. So all sequences starting with block BI and then proceeding in an arbitrary way, they describe points in this. They correspond to points in this. So for each block, I associate an interval, which is the interval of points whose sequences start with block. So for example, if you have this block, you have the decimal conversion, which is this fraction, and then since this is 4 bit, the power is 116. So this interval, which is the one here in gray, is the interval of points whose sequences are starting with 0, 1, 1, 0, 1. It's a whole notation. And then for a collection of blocks, okay, they generate certain sequences if you play with tricks. But let's say that you play k times. You concatenate those blocks k times. You can take an arbitrary concatenation of k blocks, even repeating the same block k times. But then you don't repeat blocks anymore, then you are free. Then you use even new pieces of data. You can arbitrarily continue. Okay? So Gen K of a collection is the set of sequences that start with k repetitions of those blocks, but then they continue in arbitrary. This is something we already told you. So the interval BI is this set of sequences starting with block BI, and so so means that Gen 1 means we only take one block, that's it, and then we continue in an arbitrary way. Yeah, I think that there is a measure missing. So if I take Gen 1, which is the sequence of the set of sequences in which I start with a block in my collection, and then I continue in an arbitrary way, I get a set of sequences. Then if I measure that set, there is a measure. If I measure that set, it's like measuring the union of the interval BI, because I can start with block 1, or I can start with block 2, or I can start with block 3 just once, and then I can do that. But if I start with k blocks and then I continue arbitrarily and I measure this set of sequences, so measure this here, then I measure what? The union of the intervals, but then I multiply by the measure of the set of sequences in which I was only placing k minus 1 blocks and then go ahead. This is a bit more tricky to understand, then you can substitute to this measure the union of again of the EI times the measure of the set where I place k minus 2, etc., back to Gen 1, in which they again have the measure of this union. So again, so the result is that you get the measure of the union of the interval to the power k. So if I say, to conclude, I give you the conclusion. If a block is missing, this parenthesis is a number in 0, 1. So go to stop. Now it's a very end. If a block is missing, then the union of interval is less than 1. It's less than the unit interval. So this. I know that the proof was not done in all detail, but maybe it's good to stop. Okay, here you see the designer made this, and also back to the philosophical maybe aspect. Forgetting about the technicalities. It means what? There is also part. It means that if you have a complex dynamical process, does it matter the initial conditions that you take? Yes, in time for sure. Yes, because any time computation means the two trajectory diverge. This is not the case. So two initially closed computation, they show two very different. But those two trajectories are visiting the same attractor. So the time scheduling is very different. If you take a snapshot at time 10 seconds, one trajectory is here, the other is there. So there is, as a time scheduling, they are very different. But with probability 1, they visit the same thing. But actually not with the same distribution. Both trajectory, they are different in time scheduling. They go arbitrarily close to any little neighborhood of the attractor. Yes, this is my proof. So they visit everything up to arbitrarily small distances. But maybe this is spending more time here, less time there. This is spending more time here. So the distribution, the frequency according to which you visit certain areas, they depend on the distribution. And it's actually very easy to show because those dense trajectories that you are building the bits, it's very easy to replicate. You have to, on the right, you have to place all blocks of 1 bit, all blocks of 2 bit, all blocks of 3 bit. But let's say all blocks of 1 bit, then all blocks of 2 bit, again, all blocks of 2 bit, again, all blocks of 2 bit, and I repeat a lot of time the blocks of 2 bit, and then I go only once the blocks of 3 bits. Then, of course, I'm biasing the trajectory to visit more those blocks and less other blocks. So the frequency, the distribution that you get out if you make a histogram of the trajectory depends on the way we build the sequence. That means depends on. So the answer, philosophical answer is the only thing you don't care about the initial condition is that okay, you will visit everything, but how in time and how frequent each neighborhood, that depends. Thank you. Measure 0 in where? Like we are talking about sequences in sequence. Or real or I mean I want to go to a concrete example just inside. No, here. Okay, inside lambda, inside a set of points, I have it's a countable infinity, the whole thing is still equal to zero. If it's an uncountable, you don't know it. And if it's countable, yeah, the measure of a countable union of sets is the sum of the measures of the set. That's the if it's countable. So, for example, the heteroclinics, they are given. Yeah. Yes, each set. Yes, but they have measure zero. And then they have a countable infinity of them. Ah, but what matters is that they have measure zero. So then the set of sequences missing block B is an uncountable set. So the number of sequences missing block 0, 1, 0, 0, it's an uncountable set. So in cardinality is equal to lambda, the whole thing, but the measure lambda. Then I change block B. I have block B, I have many blocks B, but it's a countable sequence. So then I take the union of all those sets, each have measure zero. Forget about that they are uncountable sets, but they have measure zero lambda. I have a countable sequence of them. I take the union because each of them has measure zero lambda. I didn't prove, I just took it right. If this is wrong, my proof is wrong. That's right. But I think it's a rather standard result.
So, the results for maps that
what does it mean? It doesn't mean
well,
nothing.
Actually,
yeah, I said yes. The proof, the answer is yes, but at least in the horseshoe equivalent dynamics. So I show this only limited to the horseshoe, but many nonlinear dynamics, even continuous time. If you take a Poincare map of many chaotic practices in continuous time, for example, the shear code, you see Smale horseshoes in the Poincare maps. So for all these processes, this proof is
with a lot of, correct.
Why? If you simulate, it's difficult to say. So you know that there are if you have a non-zero probability to get an initial condition that does not visit the world.
Usually you have assemblies, so one side of one page.
Then that's multiplicity of attractors. I'm working within the basin of attraction of what the process can have multiple attractors, as you said, but I'm only restricting myself within the basin of attraction. So all trajectories, all of them, they go the same. The question is how this trajectory will visit.
Yeah, but it can have something like the balances.
A Lorenzo system has, okay, depend on parameters, but in the typical one, there's only one. Or maybe not because we should start far away. But still, let's consider only the initial condition converging to the longest path. Among them, I think that all of them, almost all of them, visit the full butterfly. Of course, there are trajectories reaching a cycle. There are trajectories that are repeating cycles. There are tools. Are they okay? This is, I heard myself about chaotic attractors, which includes asymptotically stable, because you mentioned this word. I heard also myself of chaotic attractors, including asymptotically stable objects. But actually, to me, this violates the definition of attractor. If you take the definition of attractor, there cannot be an asymptotically stable object within an attractor. So those situations that are indeed attractors, they call them attractors, but they are not. They are attractors in a weaker sense, mirror sense, or other ways of defining them. There is not a unique way of defining attractor, but the one I'm taking here is all initial conditions in the basins produce trajectory converging to. Of course, if you have an asymptotically stable point within the attractor, being asymptotically stable, there is maybe a little basing of attraction around it. Those initial conditions in the little ball, they go to the equilibrium, they don't visit the full attractor. But because basing of attractions are open balls, by definition, the measure of that open ball is non-zero. So then it's a contradiction. Then there is a positive measure of initial condition not visiting the full attractor. But because you have this strange property of having an asymptotically stable object within an attractor in quotes, it's not actually a attractor. Yeah, it's possible. Yes. There is a full jungle of definitions. I want to stick to one. So you're right. This is already for the classical definition. So you cannot have a asymptotically stable object with